We were discussing about the packet scheduling algorithms for providing fairness as well as quality of service guarantees in internet. So what we have seen is that a fluid flow fair queuing or a generalized processor sharing algorithm guarantees fairness to the traffic queues in the sense of maximum fairness. But as we know that a fluid flow fair queuing operates only on the traffic arrivals which are considered as a fluid, and in practice the traffic arrival will be in packetized forms. So then we were looking for the packetized versions of the fair queuing algorithms. So we saw various versions. First is the round robin scheduling algorithms or the weighted round robin scheduling algorithms. Then we also saw the deficit round robin algorithms. We have seen one of the disadvantage of the weighted round robin scheduling algorithm is that it is unfair, first of all, over shorter time scales, but more than that, it requires a knowledge of the mean packet length in advance if you have to make the weighted round robin scheduling algorithms to be fair. But even then it is unfair, it may be unfair over shorter time scales. The disadvantage of having to know the mean packet size in advance was addressed in the deficit round robin by maintaining some kind of credit. But then even then the disadvantage of the deficit round robin continues to be that it is unfair, it could be unfair over shorter time scales. So then we wanted to see that what kind of packet scheduling algorithms we can derive which approximates the fluid versions of the fair queuing algorithms, that is the fluid flow fair queuing algorithms. So we were working towards that, and first we try to see that how we can keep track of the progress of the work done in the fluid flow fair queuing algorithms, okay, and accordingly then we take a decision of scheduling the packets in the packetized versions of the fluid flow fair queuing algorithms. So we define a property called a virtual time of the system. So that's what we are saying, that a virtual time is a non-decreasing function of time t, and it is a piecewise linear function with this slope dvt by dt is equal to r, okay, divided by summation over rho i's, where rho i's are the rates which have been allocated to the session I, and this summation is over the set of all sessions which are backlogged at time t, and the r is the output link rate. So we can see that the virtual time, okay, the slope of the virtual time it changes whenever the set of backlogged users changes. So essentially the slope of the virtual time is inversely proportional to the number of backlogged users. So first of all, we'll try to prove this result. How do we get this result? So let us first prove this result. Now for that, let us consider any arbitrary subinterval of the busy period. Let us consider tau to t to be any arbitrary subinterval of the busy period. So we say that consider tau to t to be any subinterval of the busy period during which no session changes states, where or during which, okay, no session changes states. Okay. So if that is so, then by definition we know that Vt minus V tau, okay, the difference of the virtual time, okay, is by definition equal to the normalized service received by the session I, where the session I is continuously backlogged during the interval tau to t. Okay. So session I is continuously backlogged is during continuously backlogged during this interval tau to t. So we have seen that the change in the virtual time of the system is equal to the normalized service received by the session I, which is a backlogged session. So now multiply both sides by rho I and sum over all the sessions which are backlogged during this interval. So we multiply by rho I and then sum it over all such I which are backlogged during this interval tau to t. So if we do this, then this becomes I belonging to b tau t, where b tau t is the set of all sessions which are backlogged during the interval tau to t, rho I wi tau t. Okay. Now we have considered this interval tau to t to be an interval where no session changes states. Okay. If that is so, then we can also write to be this equal to I belong to the set of all sessions which are backlogged, rho I wi tau to t plus rho I wi tau to t over all sessions which are absent or non backlog during the interval tau to t. Now note that the sessions which are absent during the interval tau to t, wit is actually 0 because they do not receive any normalized service. So this actually is 0 for all the sessions which belong to this set. So basically we have added 0 to this, and this means that this is also equal to sum over all I rho I wi tau t, okay, where this sum is now over set of all sessions. Remember again, tau t to be an interval where no session is changing states. Okay, so it is an interval where no session is changing state. Okay, so if you now again see in this equation, then Vt minus V tau becomes equal to rho. Now what is this? Rho I wi tau t. It is the total work done in the system during the interval tau to t, and therefore this will be equal to note that rho I summation rho I wi tau t, this is equal to the total work done in the system. Total work done in the system during this interval of tau to t, right. So therefore this becomes equal to r into t minus tau, and this tau to t, remember, is a sub interval of the busy period, and it's a work conserving scheduler, so the scheduler is continuously working. This is the interval, this is the output link rate, and therefore this is the amount of work which has been done by the scheduler. And hence from the previous equations, if you see from this equations, this becomes now equal to Ri into t minus tau. So therefore we get is Vt minus V tau, this becomes equal to R of t minus tau upon rho I, where I is the sum over the set of all backlog sessions. So this means that the slope, okay, dVt by dt, this is given by R upon summation over set of all sessions which are backlog, summation of rho i's over all sessions which are backlog. So you can see that, remember, tau to t is the interval where no session changes states. Now during such an interval where no session is changing state, the virtual time, the slope of the virtual time is inversely proportional to the number of users which are backlogged, and it is equal to Ri into summation of all the rates which have been allocated to these different sessions over the set of backlogged users. Okay, so it is equal to R upon summation rho i's. Now whenever this set changes, that means whenever one of these backlogged users becomes unbacklogged or one of the unbacklogged users become backlogged, then the slope changes. Okay, so therefore the virtual time is actually a piecewise linear function and its slope changes whenever the set of backlogged users changes. So it's something like this, that this is the slope and which is equal to r upon summation rho i's, and if some users becomes unbacklogged, then slope increases. If some users becomes more backlogged, and slope decreases, and so on. So it's a piecewise linear function. This could be an interval. This could be an interval where no session is changing state. The users which are backlogged, and the users which are non-backlogged are backlogged. Now it is at this point some session changes state, so then you go into another slope where the set has changed, okay, and so on. Okay, so therefore the virtual time Vt is a piecewise linear function, right? Now we will try to define something called as the virtual finish times. Okay, what is our objective? Our objective is trying to define the packetized versions of the fluid flow fair queuing. That is what our objective is. Now what we have done now is we have defined something called virtual time, which is keeping track of the work done in the system. How? The virtual time increases in proportion to the normalized service received by a backlogged session. Now in fluid flow fair queuing, remember that a normalized service received by all sessions which are backlogged is equal. Okay, it is equal at every instant of time. The normalized service received by all backlogged users. Okay, so therefore the virtual time, by defining the virtual time in this manner, the virtual time is keeping track of the total service which is being given by the scheduler or the server in the fluid flow fair queuing systems right now. Okay, so now we will try to attempt defining the packetized versions of this fluid flow fair queuing. Okay, so let us see. Okay, now we define some quantity which we call it to be as the virtual finish time. Let us say that Pik is the kth packet of ith session. Aik is the arrival time of the packet Pik, and Dik is the departure time of Pik in the fluid flow fair queuing. Right. This is the Dik denotes the actual departure time, is the actual time at which the packet departs in the fluid flow version of the fair queuing algorithm. Okay. Now we define some quantity, and this quantity is Fik. Okay, this quantity is for the kth packet of the ith session and defined to be V of Dik. So what it is? It is the virtual time of the system when the packet Pik departs. Okay. So at the time of departure of the kth packet of the ith session, we see what is the virtual time, and we call that virtual time to be Fik. Okay. So this we call it to be as the virtual finish time. Okay. Now first of all note that if T2 is greater than T1, okay, then Vt2 will be greater than Vt1. Virtual time is actually monotonically increasing, right? So therefore, if we schedule packets, therefore if we schedule packets in the increasing order of their virtual finish times, okay, if we schedule packets in the increasing order of the FIKs, then it is equivalent to saying that we are scheduling packets in the increasing order of their departure times in the fluid flow fair queuing, right? Because if the departure time of, let us say, kth packet of the ith session is greater than, say, lth packet of the jth session, that means if dik happens to be greater than, let us say, djl, right? Obviously, from the monotonicity property of the virtual time, okay, fik will turn out to be greater than fjl. So if I schedule the lth packet of the jth session first, okay, note that in the fluid flow fair queuing it will depart first because its departure time is less. So therefore in the fluid flow fair queuing it will depart first. So if in my packetized version, if I schedule this packet first, then I am likely to be fair. That is what I can assume. Okay. So I am proposing a packetized version of the fluid flow fair queuing algorithm, where I am saying that I define something called a virtual finish time, and the virtual finish time happens to be the virtual time in the fluid flow fair queuing system when this packet actually departs. And then I am saying that I will serve the packets in the increasing order of their virtual finish times. Now the first question of course is that if I schedule the packets in the increasing order of their virtual finish times, am I fair? Okay, that is first question. Second question is that how do I compute these virtual finish times? Okay, do I have some better way, some efficient way of computing these virtual finish time? Is there an easy way of computing the virtual finish times? Okay, so we would see that we will answer these two questions. First we will try to see how it is possible to compute the virtual finish time in a very easy recursive fashion, and then we will also prove that if we design a packet scheduling algorithm where we are scheduling packets in the increasing order of their virtual finish times, this algorithm is likely to be more fair, okay, or closer in terms of fairness to the fluid flow version of the fair queuing algorithm. So we will first see how to compute the virtual finish time in a recursive fashion. Okay, so let me just answer this question, that how to calculate virtual finish time. Let us answer this question first. Now it can be shown that this virtual finish time of the kth packet of the ith session satisfies a very easy and nice recursive relations where it is given by Lik upon rho I plus max of Fik minus 1 V of, that is the virtual time of the Pik, okay, this packet for all sessions I is equal to 1, 2, and the initial condition which is Fi0 is considered to be 0. And note that this Lik happens to be the maximum size packet, maximum oh sorry, this is the size of the, this is not the max, this is the size of the kth packet of session I. So we can see that the virtual finish times can be computed in a very easy recursive fashions. All we need to know is to keep track of the virtual time, okay, is to find out the virtual time when a particular packet arrives. And if a particular packet arrives, and if we that time look at our fluid flow, a fair queuing calculator, and from that we determine what is the virtual time when the packet arrives. If we know that, and if we plug into these equations, we can actually compute, okay, the virtual finish times of the packet. So let's try to first prove this, okay, this equation. Okay. Now let's define a quantity BIK is defined as max of AIK and DIK minus 1. That is, what is AIK? AIK is the arrival time of the kth packet of the ith session. And what is DIK minus 1? DIK minus 1 is the departure time of k minus 1th packet of the same session, ith session. Okay. Now we define this BIK quantity to be maximum of either AIK or DIK minus 1. So what is the significance of this BIK? The significance of this BIK is that the PIK, this packet, that is the kth packet of the ith session, it cannot start service, before BIK, right? It cannot start service before BIK. Why? Because either the packet has not arrived, if its arrival time happens to be higher, so either the packet has not arrived, or if AIK is less than this DIK minus 1, then the packet has arrived, but the previous packet k minus 1th packet has not yet left, so it is still in the queue. Okay. So obviously the packet PIK, it cannot start service before BIK. Okay. So actually it starts service at BIK or later in some other system, but in the fluid flow fair queuing, as soon as the packet arrives, and since it is a work conserving scheduler, okay, it will start the service immediately. So another thing is that all the previous packets of this session I must have left, okay. Must have departed by this time BIK, right. So now let us see, we define LIK minus rho I. So now when this packet, the kth packet of the ith session, that is the packet PIK, when it starts a service, the LIK is the length of the packet in bits and rho I is the rate allocated to it. So obviously this will be the normalized service received by this session during the interval for which it is backlogged. And what is that interval? That interval is extending from BIK to DIK. DIK is the time when this packet will depart. Okay. So I write this to be equal to that, this is equal to the normalized service received by the session BIK DIK. Note that the session I is continuously backlogged during the interval BIK to DIK. During that interval BIK to DIK, the session is continuously backlogged, and therefore I can write this to be virtual time at DIK minus virtual time at BIK, right. Now since now what is BIK? So I just write here in the presence of BIK. BIK is the virtual time of max of AIK into DIK minus 1. Now since we are considering during the busy period, okay, since virtual time is a monotonically increasing function during this interval, okay, during the busy period, since virtual time is monotonically increasing, during busy period, right. So since it is monotonically increasing, I can change this operator of max and V. So what I get is that Lik upon rho I is equal to, what is VDK? VDK by our definition is Fik, that is the virtual finish time, minus, if I change this, max of since virtual time is monotonically increasing, virtual time of maximum of this is same as first computing the virtual times and then taking the maximum quantity. And what is this? This is Fik minus 1. So we get this recursive equation that Fik is equal to Lik upon rho plus max of Fik minus 1, which is what this is, into V of AIK. Okay. Now what does it mean is, it means that the virtual finish times of the packet can be computed recursively. This is, this equation is easier because by definition the virtual finish time of a packet is the virtual time when the packet will depart in the fluid flow fair queuing. Now that time when the packet will actually depart in the fluid flow fair queuing system is actually difficult to determine. Okay. So we have found a recursive way of computing the virtual finish time, which states that the virtual finish time of the kth packet of the ith session can be recursively computed if you know the virtual finish time of the k minus 1th packet of the ith session and the virtual time when the packet actually arrives. When the packet actually arrives, you can easily see in the fluid flow fair queuing system what is the virtual time that is currently going on, and then plug that into these equations to timestamp a packet. Okay. So the question really is that now if I schedule the packets in the increasing order of their virtual finish times, then am I being fair? Okay. So I'll just state the result without proving it, and then if in the next lectures we'll try to prove this result. Okay. So now I'm defining a packetized versions of the scheduling algorithms. So what I'm saying is that in packetized versions of the fluid flow fair queuing algorithm, which I also call as the WFQ or weighted fair queuing, or it is also called as PGPS, as packetized generalized processor sharing. So what I am saying is that if I compute the virtual finish time times of packets and then schedule the packets in the increasing order of their finish times. So, I schedule the packets in the increasing order of their virtual finish times. It turns out that this algorithm is quite fair. How fair? Let me just state this by a result. Okay. So, let us say, so the question really is that how fair is WFQ. Let us say we define as dk to be the time at which some packet, let us say the kth packet, departs from fluid flow fair queuing. Right? dk is the time at which the packet departs under the fluid flow fair queuing. And let us say we define dk hat to be the time at which this packet departs from our WFQ. Then it can be shown that dk hat minus dk, that is the difference in their departure times, will be bounded by Lmax by R, where Lmax is the maximum size of the packet. So, what this algorithm, what the WFQ can do is that the difference between the departure times of this WFQ and the departure time had this packet been served in a bit by bit round robin manner, that is the fluid flow fair queuing, then the difference between this departure time is actually bounded, and it is bounded by Lmax by R, where Lmax is the maximum size of the packet. So, at most the difference in their departure times will be Lmax by R, where Lmax is the maximum size of the packet and not more than that. So, now here you can see that the algorithm is likely to be, let us say, unfair over an interval which is shorter than, let us say, Lmax by R, but otherwise the algorithm is likely to be fair. Okay. I mean, roughly speaking, this is what this result is trying to say, that over an interval less than Lmax by R, this algorithm is unfair. But then we can do nothing more than that in a packetized versions of the fluid flow fair queuing algorithm. In a fluid flow fair queuing algorithm, the normalized service received by backlog sessions is equal at every instant of time. This you cannot make it equal in the packetized versions, because packet is the smallest entity that you need to serve. Now we will come back to our again implementations of the WFQ and try to see, are there any complexities in terms of implementing the virtual finish times. Okay. So now what do we see in terms of computing, the complexity in the virtual finish time is that since in the WFQ, essentially what it means is that you require the computation of the virtual time, that is the VT. Okay. Now you can see that this VT, it changes slope whenever the set of backlogged users changes. So it changes its slope whenever the set of backlogged user changes. Whenever the set of backlogged users changes. So computing the virtual time means that you need to keep track of the backlogged users. Now that, which is not so difficult, because what's happening really is that a virtual time is monotonically increasing, and whenever the set of backlogged user changes, the slope of the virtual time changes. But the difficulty is that, suppose right now a packet is in service. This packet starts service at time, let's say T1, and it finishes the service at time T2. Okay. Now during this interval T1 to T2, some more packets may arrive. Now remember that we need to know the virtual time at every packet arrival, right? From this, if you see, then we need to know the virtual time at every packet arrival. Now what may happen is that during this interval, T1 to T2, when the particular packet is served, it might be possible, okay, that the set of backlogged users during any arbitrarily small interval, say T1 to T2, the set of backlogged users which may change may be of the order of the total number of sessions also, right? Because it may happen that in the fluid flow fair queuing, all sessions or a large number of sessions may finish service simultaneously. Okay. If that happens, then this set of backlogged users changes. Okay. If that changes, then the slope of the virtual time changes. Okay. So therefore, during any arbitrarily small interval of time, it might happen that the number of backlogged users, the change in the number of backlogged users may be of the order of the total number of sessions. Okay. So the breakpoints, in your virtual time slopes may be arbitrarily very large, approaching the total number of sessions. And in a typical, remember that this packet scheduling algorithms you are implementing in a router, and a typical router, the number of flows may be as large as 100,000 or even if 10,000. Then, in order to compute the virtual time, we actually then the complexity of computing the virtual time, if it approaches the total number of sessions, then the number of computations that may be required may be very large during a small interval of time, and as a result what may happen is that we may not be able to compute the finish tags or the virtual finish tags of the packets in a fast manner, and therefore our packet scheduling algorithm may not work at high speeds. Okay, so this is the major problem. Okay, now so therefore we are saying that the virtual time changes its slopes, and whenever the set of backlog and users changes, and the number of breakpoints, therefore, okay, the number of breakpoints in the VT, the slope VT can be as high as the total number of sessions, and therefore this may lead to the real time computation may be the real time computations of VT can become a problem. Right. So even though it appears that to compute the timestamp of the packet, that is the virtual finish time, we have found a very simple, nice recursive algorithms where the virtual finish time of the packet can be computed recursively by knowing the virtual finish times of the previous packets and the virtual time of the system when the packet arrives. Though we have found a very nice recursive way, even then we find that the computing the virtual time itself could be a difficult task, because the number of breakpoints can be as large as the total number of sessions, and the total number of sessions themselves can be quite large, and therefore the computation of the virtual time can be a problem. Otherwise also the computation of the virtual time is not so much of a tough task. All we need to know is that we need to keep track of the number of backlogged users. Virtual time otherwise is increasing monotonically, and whenever the set of backlogged users changes, this slope changes. Okay, but the problem really is that the set of backlogged users, the change in the set of backlogged users can be very large, and therefore the breakpoints could be very large, and therefore the real time computation of the virtual time could become difficult. Okay. Now before we go to address this problem, let me just give you an example of how actually a weighted fair queuing algorithm will work by giving you an example and computing the virtual finish times. Okay. So let's see with an example. And this example is, let's consider a very simple example where we are saying that there are 3 sessions. Now session 1, 2, 3, let's say the output link rate is, for the time being, is 1 bit per second. This session gets a packet of 1 bit, this session gets a packet of 2 bits, this session gets a packet, all at time t is equal to 0. Then we'll assume that a packet of session 2 bits arrive at time t equal to 4, right. Now if you compute the virtual finish tags of these packets, okay, so how do we compute the virtual finish tags of these packets? F11, as by giving this example of F11 is, assume the allocated rates of these row i's are all equal for them, okay. So the weights are equal, okay, which becomes equal to let's say 1 plus max of 0, which becomes equal to 1, then F21, which is equal to 2 plus max of 0, and this becomes equal to the 2, then F31, which becomes equal to, let's say, 2 plus right. So now we need to schedule the packets in the increasing order of their finish times, and we schedule the packets, first packet this of session 1, second packet of this session 2, and the third packet of this session 2. So essentially this packet gets served. So if I serve this packet, this will finish its service 1 bit per second, so at the time 1. If I serve this packet, then this packet will finish its service at time 3, and this packet will finish its service, this third packet, of time 5, because there is a tie between these two, so we can choose any arbitrary packets. So the session 1 packets get served here, okay. So this is session 1, this is session 2, this is session 3. Now note that at 4, the session, once this packet arrives, and that time I need to know what is the virtual time. So I need to know what is the virtual time at time 4, okay. This I need to compute. So let us say what's happening in the fluid flow fair queuing. So if you see in the fluid flow fair queuing, okay, this is 1 bit per second, 1/3, 1/3, 1/3 for bits will be taken up from each of the flows. So the virtual time actually increases something like this, that this is 1, 2, 3, then 4, then 5, then 6, and then 7, and so it is in. So if you see here, let's say 1, 2, and 3, and so on. So if you see So the slope of the Vt is 1/3, and this at time t, if you are serving in a fluid flow fair queuing, then the virtual time slope is 1/3, and if you see at time 3 in the fluid flow fair queuing, the session 1's bits would have been served. Now at time 3, since the session 1's bits would have been served, this session would have been completely served. Now only two sessions 2 and 3 are backlogged, and therefore it changes its slope. So now it becomes half. It becomes half till about 4. So till about 4, and at that time the value of the virtual time, therefore, so note that this slope is 1/3, okay, of the virtual time. So the slope here is 1/3. Now this slope changes, and the slope becomes half. So at time 4, the second packet at the session 1 has arrived, and at that time the value of the virtual time will be 1.5. So we wanted to know this, what is the virtual time at time 4. So this is actually, we determine that 1.5. So if it is 1.5, and if you wanted to calculate F12, that is the finish time of the second packet of the first sessions, that becomes equal to a packet of length 2 arrives. So 2 plus max of the finish time of the previous packet, which was 1.5. So this becomes equal to 3.5. So obviously this is less than the finish time. So this is greater than the finish times of either of these, that is the third session. So therefore this packet only is likely to be served in the packet scheduling algorithms. Now let's look at again. Now after this, what happens? The packet has arrived at in the first session also. So the slope changes again, and the slope now becomes equal to 1/3, and at this point it becomes 1/3 again, and at this point at 5.5 here, both the sessions, that is session 2 and session 3, they are completely served, and after this the slope becomes 1 because only the user 1 is now backlogged. So at this point the slope again becomes 1/3 from 4 to 5.5 slope again, and then at this point remember that both the sessions, that is the session 2 and 3, they have been served completely, they are both bits, and then only this session is remaining backlogged with the packet 2. So therefore this slope becomes now slope is 1, and this packet finishes service at 0.7. So this way this slope is 1. So we can see that this way the virtual time changes its slope whenever the set of backlogged users changes. So here I just wanted to clarify here that even though in our previous equations that we had considered that a virtual finish time is given by Lik upon rho I, where rho I is the set of is the allocated rate, okay, is the allocated rate, okay. But in computing this virtual finish times here, I have taken these rho i's of all the 3 users to be 1. Essentially they are considered as the weights, okay. So I have given them the weights of 1, 1, 1, which means that all the 3 users have been allocated equal rates. So I have not considered the specific values of rho i's. In place of rho i's, you could also consider the weights, the different weights which have been given to the 3 individual sessions, okay. So I mean that is the minor point that I want to make here, because the particular example that I have considered really I have illustrated it by considering that different weights have been given to them, and they are not actually in terms of the allocated rate, okay. So weights I have considered. So the weights and the rates, okay, they do not make sort of much distinction in terms of computing the virtual finish times. alright. So this gives an example and also an idea how to compute the virtual finish time. So I again want to reiterate that what we were discussing is what we thought is that we wanted to have an algorithm which is which approximates the fairness character of the fair queuing algorithm. So we consider both the weighted round robin or the deficit round robin and found them to be approximate versions of the fluid flow fair queuing algorithms, but not so fair as we would like to be. Then we considered these packetized versions of the fluid flow fair queuing algorithms, which we called as the weighted fair queuing algorithms, and we saw that we can derive a fair version of the packetized fluid flow fair queuing algorithm, provided if we keep track of the actual work done in the system of the fluid flow fair queuing and then schedule the packets in the order of their virtual finish times, and we can see that this algorithm is fair in the sense that the difference between the departure times in the packetized versions and the fluid flow fair queuing versions will remain bounded by the maximum size of the packet divided by the output link capacity. So it turns out to be very close to the fair queuing algorithm in terms of fairness, but the problem remains that we need to compute the virtual time for the implementations of the weighted fair queuing algorithms, and computing the virtual time actually requires keeping track of the set of backlogged users, and that can pose a problem in terms of the real time computations. So we should look for algorithms which can address these problems in the sense that the real time computation of the virtual time can become easier, and at the same time we retain the basic characteristics of the fairness of the packetized versions of the scheduling algorithms. So that we will address in the subsequent lectures.